Hey there, curious minds. Welcome to the Deep Dive. We're the place that takes your stack of sources, digs through them, and pulls out the insights you need to be, well, truly well informed. Today, we're diving deep into something that's really changing how machines perceive our world: convolutional neural networks. You'll often hear them called CNNs.
That's right. It's fundamental technology.
Absolutely. Think about the facial recognition that unlocks your phone,
hmm
or how your photo albums get sorted automatically, even self-driving cars seeing the road.
All powered by this AI ability to, interpret images.
Exactly. So our mission today is to unpack the architecture behind this revolution in computer vision. We want to understand what they can do, things like facial recognition, image classification, but also, maybe more importantly, look at their surprising limitations.
Yeah, the blind spots are fascinating too.
Totally. And we've got some great source material to guide us. We're looking at the 100-page machine learning book by Andrei Burkov, and also Martin Ford's Architects of Intelligence, which has insights from, well, the pioneers themselves, people like Yann LeCun, Geoffrey Hinton, Fei-Fei Li.
Some real heavyweights in the field.
Definitely. Okay, let's get into it.
What's really interesting is that this idea of machine seeing, it's not actually that new.
Right. It goes way back.
Way back to the 1950s, really, with the first artificial neural networks. These were attempts to roughly emulate biological neurons.
Yeah, our sources talk about Frank Rosenblatt and the perceptron from the late 50s.
The perceptron, classic.
It's described as this, simple system, right? Numerical inputs, weights on those inputs.
And then it sums them up.
Yeah, sums them up. And if it hits a threshold, it outputs a 1, otherwise a 0, like a neuron firing, basically.
A very simplified model, but yeah.
And Rosenblatt, he was incredibly optimistic back then, even in 1958. He predicted computers that could, and I'm quoting here, walk, talk, see, write, reproduce itself, and be conscious of its existence.
Wow. That's ambitious for 58.
Seriously. And even recognize people and call out their names. It sounds like science fiction almost.
It really does.
Yeah.
But that initial excitement around these simple perceptrons didn't last too long.
No, it hit a wall.
It did. Marvin Minsky's critiques in the 60s were pretty influential. He pointed out some fundamental limitations, especially regarding training networks with multiple layers.
Which turned out to be crucial later on.
Absolutely crucial. But his work contributed to, well, neural networks falling out of favor for a while.
Yeah.
Symbolic AI became more dominant. It led to what people call an AI winter for this kind of research.
A winter, right. But the idea didn't completely die out.
No, thankfully not. People like Yann LeCun, mentioned in our sources, they kept working on it, even through that quieter period.
And that persistence led to refining a key learning method, right? Backpropagation.
Exactly. Backpropagation was the breakthrough needed to efficiently train those deeper, multi-layered networks. That's really what unlocked the door to what we now call deep learning.
Okay, so deep learning, that's the term we hear everywhere now.
It really is. It's the engine behind the recent AI boom, especially in things like image and facial recognition. It's all about these deep neural network software structures inspired by the brain's layered processing.
And for vision specifically, the star player is the convolutional neural network, the ConVet or CNN.
Precisely. Our sources explain them as having this sequence of layers, simulated neurons or units. When an image goes in, the units in one layer feed input to the next.
Okay, so far so good. But what makes them convolutional? What's special there?
That's the key difference from older types of networks. Instead of every neuron connecting to every neuron in the next layer, which gets computationally massive very quickly.
Right, I can imagine.
CNNs use these things called filters or kernels. You can sort of picture them like tiny magnifying glasses or feature detectors that slide across the input image.
Sliding across. Okay. Looking for what?
Each filter is designed to spot a very specific, simple pattern. It could be a vertical edge, a horizontal line, a particular texture, maybe a corner, very basic visual elements.
So it's scanning locally, not looking at the whole picture at once initially.
Exactly. The scanning process is the convolution. As the filter moves, it performs a calculation, and the output is what's called a feature map. It's like a new version of the image that highlights where that specific pattern was found.
Interesting. And this is more efficient.
Much more efficient.
Yeah.
Because you use the same filter across the whole image that's called parameter sharing. It dramatically reduces the number of connections the network needs to learn.
Got it. So layer 1 finds simple edges and lines. Then what?
Well, often the output from that convolutional layer, the feature map, goes into something called a pooling layer. Yeah, pooling layers basically shrink the feature map down, making it smaller while keeping the most important information. It might take the maximum value from a small patch, for instance. This helps make the network a bit more robust if the feature shifts slightly in the image.
Like distilling the key signals.
Kinda, yeah. And this sequence convolution, then maybe pooling gets repeated, layer after layer.
Building up complexity.
Exactly. Early layers detect simple stuff, edges, textures. Later layers take those feature maps as input and combine those simple features to recognize more complex shapes, maybe an eye or a nose or the curve of a wheel.
And eventually.
Eventually, deep enough in the network, these combined features allow it to recognize whole objects, a cat, a dog, a car, that handwritten 8 we mentioned.
So it's learning a hierarchy of features, from pixels to concepts.
That's a perfect way to put it. It builds understanding step by step.
And you mentioned earlier, Fei Fei Lai points to 2012 as a real turning point.
Yes, a convergence.
What came together then?
3 main things, really. 1, massive labeled data sets, especially ImageNet. Millions of images categorized.
The raw material for learning.
Absolutely. 2, the rise of GPUs, graphics processing units. They turned out to be incredibly good at the kind of parallel math these networks need. Made training feasible on a large scale.
Faster computers, basically.
Much faster for this specific type of task. And 3, the refinement of the CNN algorithms themselves, thanks to pioneers like Geoffrey Hinton and his students. The algorithms were ready, the data was there, the computing power arrived. Boom.
The perfect storm for AI vision. And that layered structure, as Barbara Gerst points out, that's why it's called deep learning, right? Just lots of layers.
Precisely. It's about architectural depth, not necessarily philosophical depth,
Yeah.
although the results can feel quite profound sometimes.
No kidding. The success has been pretty astonishing. Our sources highlight how ubiquitous CNNs are now. Google, Facebook, Microsoft, Amazon.
They all rely heavily on them for image recognition, facial recognition, content moderation, you name it.
And that ImageNet challenge you mentioned, the competition, that really pushed things forward.
Oh, massively. It started in 2010. Programs had to classify objects and images across 1,000 different categories. It was incredibly hard at first.
But the progress was rapid.
Extremely rapid. By 2015, you had teams from Baidu, Microsoft, Google, all achieving accuracy rates over 95%, even arguably surpassing human performance on that specific task. They were fighting over tiny fractions of a percentage point.
Wow. It really shows their power in object recognition.
Definitely. But it's gone beyond just naming objects.
Right, you mean describing them, like image caption.
Exactly. Systems like Google's Show and Tell or Microsoft's Caption Bot, you give them a picture, they generate a sentence describing it.
Which is incredible, though Yoshua Bengio does note they can sometimes be way off the mark.
Sure, they make mistakes, sometimes funny ones. But as Bengio also said, the fact that they were able to reach the level of performance that they have was not something we expected. It was a surprising leap.
Bridging vision and language like that.
Yeah. And beyond just vision tasks, CNNs are components in bigger AI systems too.
Like AlphaGo.
Like AlphaGo, precisely. The system that beat the World Go champion. It used CNNs to analyze the board, to evaluate positions. It learned patterns that looked almost like intuition.
So it wasn't just calculating moves, it was seeing the state of the game in a sophisticated way.
In a sense, yes. Learning from millions of games to recognize advantageous patterns.
So pulling this together, what does it mean for, us? For everyday life?
It means AI can process and understand visual data at a scale and speed humans just can't match. Your phone gets smarter, search becomes more visual.
And potentially huge applications in areas like medicine, analyzing scans.
Absolutely. There's a lot of research into using CNNs to help radiologists detect signs of disease, like cancer, in medical images, potentially catching things earlier or more consistently.
Okay, so the capabilities are impressive. But it's not all smooth sailing, is it? There are downsides, limitations.
Definitely. And this is where it gets really interesting and maybe a bit concerning.
Our sources point to a major one, the dependence on data. Andrew Ng warns about this reliance on massive quantities of human-labeled data.
Right. These systems need to see thousands, sometimes millions, of examples of something to learn it well. Humans can often learn from just 1 or 2 examples.
That's a huge difference.
It is, and Yoshua Bengio echoes this. We can't realistically label everything in the world and meticulously explain every last detail to the computer.
Which leads to the long tail problem.
Exactly. There are countless rare events or unusual objects that just don't appear often enough in the training data. A self-driving car might be great in common scenarios, but what about that really weird thing it's never seen before?
Like your example of a giant tumbleweed or an oddly placed obstacle.
Yeah. It hasn't been explicitly trained for that edge case because labeled examples are scarce or non-existent.
And then there's the the fragility, the weird ways they can be fooled.
Ah, yes. Adversarial examples. This is pretty mind-bending stuff.
Tell us about that. The sources describe things like special eyeglass frames.
Right. Researchers designed patterns, printed them on regular glasses frames, and when someone wore them, it could trick a state-of-the-art facial recognition system into thinking they were someone else entirely,
With high confidence.
with high confidence.
Huh.
Or tiny stickers placed on a stop sign that could cause a self-driving car's vision system to classify it as, say, a speed limit sign.
That's unsettling, especially for safety-critical systems.
It really is. And it even applies to medical imaging. Subtle noise patterns, totally invisible to a human radiologist, can be added to an image to make the AI flip its diagnosis, say, from confidently predicting no cancer to confidently predicting cancer.
How is that even possible if a human can't see the change?
It gets back to how these networks learn. They learn what it observes in the data rather than what you, the human, might observe.
Mhm.
They might latch on to superficial statistical patterns or textures that are correlated with the answer in the training data, but are the actual features we humans use to reason.
So they're finding shortcuts, almost.
Sometimes, yes. Shortcuts that work incredibly well on the training data, but are brittle and fail unexpectedly when the input is slightly different or maliciously crafted. Their perception is just fundamentally different from ours. They lack our ability to abstract and generalize robustly.
Which raises huge questions. If a system can be fooled by a sticker, Gary Marcus's point seems valid. They don't have the common sense or abstraction needed for the messy real world.
It highlights a gap between pattern recognition, which they're amazing at, and genuine understanding, which is still far off.
So where does this leave us? What's the takeaway on how AI sees the future?
Well, we've seen CNNs are incredibly powerful tools. They've revolutionized computer vision, facial recognition, image classification, huge impact.
No doubt, they're everywhere.
But, as experts like Stuart Russell and Arnett Cioni remind us, there's still just one tool in the toolbox. A very effective tool for supervised learning on large data sets, but not the whole story of intelligence.
Right. So achieving true visual intelligence like humans have, with understanding, abstraction, common sense, that's still an open challenge.
Very much so. It seems it will require more than just bigger data sets and deeper networks. We need fundamental breakthroughs in how machines learn, reason, and maybe even perceive cause and effect.
And it's still a bit of an art. Demis Hassabis and Eric Horvitz call tuning these networks alchemy.
Yeah, there's still a lot of human intuition and expertise involved in getting these things to work well. It's not quite a standardized engineering discipline yet at the highest levels.
So it leaves us with a really interesting thought, doesn't it? If these AI systems can see in ways that are simultaneously superhumanly precise for some things,
And yet surprisingly naive or brittle for others.
what does that actually tell us about perception itself, ours included, and what kind of responsibility do we have when building systems that see the world to ensure they move beyond just recognizing patterns toward something closer to understanding?
That's the big question hanging over the field, I think.
Well, thanks for diving deep with us today. Hopefully you listening feel a bit more well-informed about the amazing and sometimes puzzling world of AI vision and CNNs.
Hope it was insightful.
Until next time, keep questioning, keep learning, and maybe look at the world around you and how you see it with fresh eyes.